All right, let's talk about grabbing the steering wheel of our network. Today, we're diving into a really fundamental skill, static routing. It's all about manually telling our data exactly where to go, giving us this incredible, precise control over our network's paths. So, let's get right into it.
So picture this. This is a super classic setup, right? We've got our local router, R1, and it's connected to our whole local network. But it needs to get out to the big wide world of the internet through our provider, R2. The thing is, without any instructions, R1 has absolutely no clue how to reach, well, anywhere. It's totally up to us to give it the map.
And that really is the big question, isn't it? I mean, we've got all this amazing automation, all these dynamic protocols that can literally learn the network all by themselves. So why on earth would a network engineer choose to manually carve out a path? It might seem a little old school, but trust me, there are some very, very powerful reasons to do it.
Okay, so let's just tackle that question head on. This whole first section is all about the why. What are the strategic advantages of choosing that manual path and actually putting static routes into place?
Here's the side-by-side breakdown. Static routing really shines in certain situations, especially for what we call stub networks. Those are just simple networks that only have one way in and one way out. Because there are no chatty routing updates being broadcast all over the place, it uses literally zero bandwidth for overhead. And from a security perspective, the routes aren't advertised, which makes the path super predictable and a whole lot less vulnerable. Bottom line, it's lean, it's efficient, and it is precise.
All right, so we've got the why down. Now let's get into the what. How do we actually speak the router's language and configure one of these static routes? It all really boils down to just a single command.
And this is the blueprint right here. For IPv4, we're talking IP route, and for IPv6, IPv6 route. The command really has three main ingredients. First, the destination network. Basically, where are we trying to go? Second, the filter, which is the subnet mask or prefix length. How specific is this destination we're aiming for? And third, the forwarding parameter. How do we actually get there? And this last part is where things get interesting, because we have a few options.
So about that forwarding parameter, there are really three ways to point a packet in the right direction. We can give it a next hop IP address, which makes the router do a second lookup. We call that a recursive lookup to find the right exit interface. Or we can just tell it which exit interface to use. Or, for the most precision possible, we can specify both. Each one of these has its own perfect use case.
Let's start with the one you're going to see the most, the next hop approach. All we do here is tell our router, R1, the IP address of the very next router in the path. In this case, 172.16.2.2. The router then does a quick lookup to figure out which of its own interfaces it needs to use to reach that IP. This is, without a doubt, the absolute best practice for multi-access networks like Ethernet.
Okay, next up is the directly connected route. This is where we only specify the exit interface, like serial 0/1/0. This works like a charm on point-to-point links where there's only one other device on the other end. But, and listen up, this is a huge warning, never ever use this method on an Ethernet network. It forces the router to send out an ARP request, which is basically a broadcast shouting, "Who has this MAC address?" for every single packet. That can absolutely cripple your network's performance. Seriously.
And that brings us to the fully specified route. So what if your router, R1, is connected to a switch that has a bunch of other routers plugged into it? If we just use the exit interface, R1 has no idea which of those neighbors is the correct one to forward the packet to. So by providing both the exit interface and the next hop IP, we completely eliminate any ambiguity. This gives us that absolute pinpoint precision we were talking about.
So after we type in our command, how do we actually know it worked? Well, we check the map. And the map is the routing table. The command show IP route tells us everything. You can see that little S code right there? That stands for static. You'll also see the administrative distance. That's just a measure of how trustworthy a route is. And it's 1 by default for static routes. And of course, how to get there, via the next hop IP address.
Okay, theory is great and all, but let's talk about how we use this in the real world. Let's solve one of the most common networking problems out there, giving our local network a gateway to the entire internet.
I mean, really think about that for a second. The global internet routing table has close to 1 million routes. There's no way you could possibly program all of those into your little local router. It would run out of memory in an instant. So, what do we do? How do we handle this?
The solution is actually beautiful in its simplicity. It's called the default route. Instead of trying to learn almost a million internet routes, our stub router just follows one simple rule. If a destination isn't already in my local routing table, just send the packet to my ISP and let them figure it out. This makes our ISP router our gateway of last resort. And we configure this catch-all route using a pretty special address. For IPv4, we call it the quad 0 route, 00000000, which basically means match any network. For IPv6, it's even simpler, CC through 0. By just pointing this single route to our ISP, we've given our entire network access to the internet. It's that easy.
All right, so now we have a path to the internet. That's great, but let's make it resilient. What happens if our main connection goes down? We need a backup plan. We need a spare tire for our network.
This is the kind of scenario that keeps network admins up at night. If that primary link to the ISP gets cut, does your whole business grind to a halt? Well, not if you've planned ahead with a very special kind of static route.
And that brings us to the floating static route. The logic here all comes down to that administrative distance, or AD, that we saw a minute ago. Just remember, the lower the number, the better. It's more trustworthy. Our primary route has that default AD of 1. What we do is configure a second static route through a backup link, but we manually give it a higher AD, something like 5. The router will always prefer the AD1 route, keeping our backup route hidden, until the moment it's needed.
And here is where the magic happens. Look at phase 1. Everything's running normally. The routing table clearly shows the primary path with its AD of 1. But when that link fails, that AD1 route just vanishes from the table. And instantly, the backup route with the AD of 5 floats up to become the new active route. The failover is completely automatic. It's just an incredibly elegant way to build redundancy into your network.
So we've covered the fundamentals and some really powerful ways to use them. Now let's wrap up with a few advanced techniques and best practices that'll help you really master static routing.
You know, sometimes you don't want to route to an entire network. You want to route to a single specific device. This is what we call a host route. By using a /32 mask in IPv4 or a /128 in IPv6, we're basically taking a sniper approach, creating a path to just one specific IP address. This is perfect for things like high-security links to a critical server, or for important management traffic.
Now here is a common trap that people fall into in the IPv6 world. IPv6 link local addresses, the ones that start with FE80, are only unique on a single link. So, your router might have two different neighbors on two totally different interfaces, but they could both have the exact same link local address. To avoid any confusion, you must use a fully specified route, telling the router both the exit interface and the next hop link local IP.
Okay, let's wrap this all up with a quick cheat sheet. For Ethernet, always use the next hop IP. For those old-school point-to-point serial links, just use the exit interface. For backup paths, create a floating route by setting the administrative distance higher than 1. For internet access from a simple stub network, use a default route. And finally, for IPv6 link local addresses, you must always use a fully specified route.
And really, that's the final takeaway here. Static routing gives you the pinnacle of manual control, predictability, and efficiency, especially for smaller, stable networks. But that manual nature is also its biggest weakness. So the question I want to leave you with is this. What happens when control just isn't enough and you need your network to be dynamic, adaptive, and able to scale on its own? Well, that's where we step into the incredible world of dynamic routing protocols.